Okay, for unit 7, we will continue on with the topic of free radicals reaction. So in this unit, we will see the reactions of alkene with halogen. So basically, we are trying to substitute the hydrogens in the alkene with a halogen group. Okay, so another name for this reaction may also be known as free radical substitution reaction. So the objective for this unit will be you should be able to explain the concept of bond breaking and also types of reagent that is needed for the reaction to occur. And then we will see the reactions of alkanes and also the mechanism of the free radical substitution reactions. So basically, for an alkenes, being a very stable organic compound, so it doesn't undergo a lot of reactions. Okay, um, first, the reaction that alkene can undergo is the reaction in the absence of oxygens. So without the presence of oxygen, this C-C bond, okay, carbon-carbon bond and also carbon-hydrogen bonds are very strong. Okay, the energy needed to break these bonds are around 300 to 400 kilojoule per mole. Okay, and these are also examples of non-polar bonds. Okay, being non-polar or covalent bonds, okay, they can only be broken under extreme conditions. Okay, for example, you need to heat up to around 800 degrees Celsius, okay, to convert long chain alkene to shorter chain alkene and alkene. So meaning if you have like a carbon 20 alkene chain and you want to uh, convert it into shorter chain length for like hexane or butane, so you need to heat the whole thing up to around 800 degrees Celsius. Okay, this is what we call as thermal cracking. So in petroleum industries, okay, this is what is done to convert all these long chain alkene into petroleum products, okay, from crude oil to petroleum products. So another term we call it as thermal cracking. Okay, just by using heat, these long chain alkene are being converted into shorter chain. And then the second type of reaction is the reaction of alkene in the presence of oxygen. So this is basically a combustion reaction. Okay, so reaction with oxygen occurs during combustion in an engine or flame when the alkene is used as fuel. So example, if you fill up gas in our car, the engine will require some of uh, what you call this alkene, the mixture of alkene to be burned. Okay, the energy release is what drive the engine and also your car eventually. So carbon dioxide and water are formed as products, and a large amount of heat is released. So this heat uh, is correspond to the energy. Okay, it can be converted into energy. And then we have the reaction of alkenes with halogens. So for this type of reaction, only bromination and also chlorination, which are important under lab conditions. So for small scale, only bromination and chlorination can be done. So let's look at the reaction over here. So consider the reaction between methane and chlorine gas, Cl2. So CH4 plus Cl2 should give you CH3Cl or chloromethane plus HCl as the product. But this reaction cannot simply proceed, okay, without the use of the correct reaction environment, okay, because if you look here, we have the first step, which is called the initiation step. Okay, what happened in the initiation step is, here we have the CH bond strength is around 413 kilojoule per mole, while the chlorine-chlorine bond strength is much lower than that, okay, almost half than the CH bond strength. So therefore, the first step would be the dissociation of the weaker CSL bond, meaning this will be broken first. And this uh, falls under the homolytic fission, okay, because the electrons are going to be shared equally between the two chlorine. So the energy of this reaction could be supplied by either, okay, you can have two choice, one UV light or just plain sunlight, okay, and it can be symbolized in the reaction as UV or this symbol H nu, okay, or if you don't have this source of UV light, okay, you may also supply heat, okay, which correspond to the energy around 300 to 400 degrees Celsius. So this energy can be used to break the Cl-Cl bond. Okay, so the first step, we want to break the Cl-Cl bond. Okay, not the CH bond, because we want to break this CH bond, the energy needed will be much higher than 400 degrees Celsius. Okay, the temperature. So once this Cl-Cl bond, okay, they are going to proceed with homolytic fission. So each of the chlorine will receive one electron. And what you are going to end up with is two chlorine free radicals. So this is the free radicals, okay, hence the free radicals substitution reactions. So once you have this chlorine free radical, then only it can proceed to the second step, okay, which what we call as the propagation. So being a radical, that chlorine will be very high in energy and also prefers to react, meaning it is unstable. So the high energy free radical chlorine may now start the reaction. So in propagation steps, the reaction mechanism can be seen that a small initial input of radicals is sufficient to bring about the reaction of very many molecules of hydrogen and methane. So this is what we call as chain reaction. So what happened over here, if you look at the mechanism, so this is the mechanism. You have the chlorine free radical and your alkene. So what will happen is the chlorine free radical will uh, take one of the hydrogen from the alkene. Okay, when it takes this hydrogen, okay, the carbon instead now end up being a free radical. So because the chlorine already took one of the hydrogen, so it becomes HCl. It is no longer a free radical, but carbon now become a free radical. Then what happened once you have this CH3, okay, the carbon become free radical, it reacts with another chlorine molecule, okay, Cl2 molecules. Okay, because when you do a reaction, there will be not just only one CH4 and one Cl2, okay? You are going to put maybe probably 1 mole of each of the reactant, for example, and inside that 1 mole, there will be many molecules. Okay, so CH3 plus Cl2, and you are going to end up with the product, which is the CHTCl, which is an alkyl halide. So this carbon free radical will attack one of the chlorine, so it will take one of the chlorine, and what will happen is you have these chlorine free radical bags. Okay, so but the initiation step is just needed to produce chlorine radical. Once you have that chlorine radical, it can be used to uh, proceed with the propagation step. Okay, just by having one chlorine radical, it can start with the whole reactions. Okay, once the product is formed and you have this Cl radical, it can go back to step number 1, meaning it will repeat again and again until all of the reactant has been reacted, for example. Okay, so this is what we call as the chain reaction step, because it happens again and again. So in halogenation, the chain reaction will continue to the order of 10,000 cycles before the radicals start combining. So this is the same like this one, but with the movement of electron, okay, being shown. So here you have half arrow, and this one also you have half arrow, okay. And then on to the last step, which is the chain termination step. So this is the final step in the free radicals substitution reaction. So what happened here is when any two free radicals combine, the chain reaction comes to terminate, meaning at the end of the reaction. So you have Cl free radical combined to become Cl2, and then you have this carbon free radical with the carbon free radical combining to become another type of alkene, and with the last one is the formation of the product itself, which is the CH3 and the CH3 free radicals and the Cl free radicals. Okay, but the overall reaction will be written as your alkene, in this case CH4 or methane, plus Cl in the presence of heat or UV light to obtain your alkyl halide plus HCl. Okay, the halogen can be either chlorine or bromine. Okay, in terms of the reactivity and stability, the reaction does not stop at chloromethane only. Okay, because as the concentration of this chlorinated product increasing, the hydrogen abstraction may occur from this molecule as well to give the chloromethane. So what happened over here? So the reaction has already completed, meaning that the products that you want has already been formed, but you still have these chlorine radicals, and instead of reacting with the initial reactant or initial substrates of alkene, it reacts with the product that just has been formed, okay, which is an alkyl halide. So what will happen here is that one of the hydrogen will get replaced again. So the product that you are going to end up with is CH2Cl2. This happened because as the reaction proceeds, okay, the CH4 concentration will be lower, while the CH3Cl concentration will be increasing as more product will be formed, okay, as times proceed, as the reaction proceeds. So that's why the Cl free radical ends up reacting with the product, okay, instead of just the reactant of CH4 exclusively. So as the concentration of dichloromethane goes up, okay, dichloromethane is CH2Cl2, it may also react, and so the overall reaction could be expressed as you have CH4. In the presence of excess Cl2, you will produce CH3Cl, and then another substitution, CH2Cl2, dichloromethane, another substitution of chloroform, CHCl3 plus tetrachlorocarbon, CCl4. Okay, so this is what you are going to end up with if only you have excess chlorine presence in the reaction. But if the amount of chlorine is just sufficient enough to convert this CH4 to CH3Cl, then you will not have any of this other product. Okay, so the four chlorinated hydrocarbons may be separated easily by fractional distillation because each of these compounds have different boiling point. So you may just heat, okay, and then it will turn into vapor, into gas, and you can condense it back to be separated. So the actual ratio of products will depend on the relative amounts of chlorine and methane used. So excess chlorine, you're going to end up with more CCl4 here, but if more of the alkene is used, which is the CH4, so you are going to get with just one substitution, which is the CH3Cl. Okay. So this halogenation substitution for alkene can also occur for bromine, but not quite as readily compared to chlorine. Okay, the reaction does not occur at all for iodine because the first propagation step is highly endothermic and the reaction is irreversible. So endothermic means the reaction absorbs energy. So for iodine, if you want to convert it to into iodine free radical, you need a very large amount of energy. So just like just now for chlorine, the ClCl bond needed around 234 kilojoule per mole of energy to break it. But for iodine, it is much more than that. So that's why it's not suitable to be done in lab scale. While for fluorine, the reaction is highly exothermic, meaning it releases energy. So when it releases energy, there is a possibility it may cause explosion because release energy, temperature will end up increasing. It will be increased, but up to a point when there's too much energy being released at the same time, so explosion can happen. So the reaction will be more complicated with higher alkanes. The higher alkanes meaning you have C14, for example, and if the alkanes has branching. So because of the large number of products which can be formed. Okay, for example, here we have a pentane, 1, 2, 3, 4, 5, 5 carbon pentane, and then I want to subject it to chlorination. So products formed will be, here we have 3 different products, meaning that if you look at the first product, the chlorine is being substituted at the terminal carbon. Okay, and then the second product, the chlorine is being substituted at the second carbon, while the third product, chlorine, will be substituted at the third carbon. So there are 3 possibilities in terms of what kind of product will be formed. So how are we going to determine which hydrogen will be abstract first? Okay, whether this one or this one or this one. So that there is actually a rule in which hydrogen you must select first. Okay, so here we have this ease of removal of hydrogen, meaning which hydrogen can be easily removed first by the chlorine free radical just now. So we just have to follow these rules. The first one state that remove hydrogen from carbon that is attached to a heteroatom. So heteroatom is any other atom besides carbon and hydrogen, and it must be in the chain itself, meaning that it is not just substituents, okay, like C double bond O or OH, for example. So it must be in the alkyl chain. And then second one will be you have to remove hydrogen from carbon that is attached to the C double bond C, okay, either allylic or benzylic, and you have to follow the tertiary, secondary, and primary if there is more than one type of C double bond C. And the last one will be the removal of hydrogen from carbon according to the most stable carbon free radical form, which is tertiary, secondary, and primary. So if you look at this example over here, uh, uh, the first hydrogen that will be removed. So if you look, the hydrogen is not being drawn, okay, because this is just normal skeletal structures. But you know that each carbon must have 4 bonds. So this is carbon. It is bonded to only one other carbon. So that means you have 3 hydrogen over here, 2 hydrogen here. This one, 1 hydrogen, 3 hydrogen, 2 hydrogen, 2 hydrogen, 1 hydrogen. This one, no hydrogen at all. 3 hydrogen, 3 hydrogen, 3 hydrogen, 3 hydrogen, and this is only 1 hydrogen. This one also 1. So The number one, okay, the first hydrogen that should be removed is located at this carbon. So why? Because the first rule state that remove hydrogen from carbon that is attached to a heteroatom. So carbon that is attached to heteroatom. So if you look in the structure, we have oxygen. So that is the heteroatom. So which are the other carbon that is attached to heteroatom? You have 1 and 2. So you have these two carbon over here. And among these two carbon, you have to choose according to the tertiary, secondary, and primary. Tertiary being the most stable. So between these two, this is considered to be primary because it is bonded to only one other carbon, while this carbon is bonded to 1 and 2. So this is secondary. So secondary takes priority, then primary. So you have 1 and number 2. And then number 3 is over here, and number 4 is over here, because according to the second rule, remove hydrogen from carbon that is attached to C double bond C. So where is your C double bond C? You have C double bond C here, and there are 1, 2, 3 carbon that is bonded to the C double bond C. So once you have established that, you have to remove the hydrogen according to the stability of the free radical that is going to be formed, which is tertiary, secondary, and primary. So this carbon is secondary because it is bonded to 1, 2 carbon. This one is primary. Okay, it is bonded to only this carbon, while this carbon over here is bonded to 3 other carbon. You have 1, 2, and 3. So tertiary, secondary, primary. So number 3, number 4, and number 5. And then the last one will be to remove hydrogen from carbon just according to whether it is tertiary, secondary, or primary. So you have this one, okay, this one, and all of the terminal carbon. So this is secondary, 1 and 2. This is tertiary, 1, 2, and 3. While all of this is primary. So tertiary first, number 6, secondary, number 7, and all the other one are considered to be equal because they are primary, they will form primary carbon-free radical. Then example of how you can apply the reaction or the free radical reactions. So basically, it is commonly used for hydrogenation of allylic or benzylic hydrogenation. So benzylic involve benzene structures, but allylic, it must involve a C double bond C in these structures. Okay, this probably will be covered in next semester's subject. As the radicals form will be more stable to a heteroatom, which is N and O. So if you look at this example over here, we have cyclopentene, pentene, okay, a cyclic structures with double bond, cyclopentene. And on to this side, if you provide bromine or you subject it to bromine without the presence of UV light, meaning you done this reaction in dark, okay, no lights whatsoever, then you are going to end up with this product. You have bromine attached to both of these carbon, the double bond will be broken. But if you are doing the reactions in the presence of UV light, okay, or maybe you supply heat to the reactions, okay, you are going to end up with this radical substitution reaction. You have bromine attached to this carbon while the C double bond C remain intact. Okay, so this is an example of electrophilic addition reaction. So this is an addition reaction in which the double bond will be broken, while this one is a free radical substitution reactions. So if you look at where this bromine is added, it actually follows the same rule over here, which is the second one. Remove hydrogen from C that is attached to C double bond C. So this is C double bond C, and you have 2 other carbons. So these 2 other carbons are considered to be in the same environment, okay, to be equal. So you can have the bromine substitute the hydrogen at this carbon, or at this carbon. All right, so that will be all on this chapter. So there are some other videos also I have provided in the Google Classroom. So please try to view them, and we'll continue with Unit 8 next week. All right, thank you.